Okay, so welcome back. Now, in this video, here's the theorem. That's basically the result of what we were talking about in the last video about having a sequence that converges to a particular limit, particular number, and having a function that is also continuous at that limit. And then being able to then say, hey, the function evaluated at the nth term, the limit of that function approaches the function evaluated at the limit. Okay? So with that being said, here's the theorem that comes from. It says, consider a sequence a sub n, and suppose there exists a real number L such that the sequence converges to L. Okay? So again, we're starting with an assumption that we have a sequence and that sequence converges to a number L. Further, suppose that f is a continuous function at that limit L. Okay, so those are the two assumptions. So if those conditions are met, then there has to exist an integer n. Is it an integer? It should be a positive integer. Yeah, usually a positive integer. Okay? Such that f is defined at all values of a sub n for n greater than or equal to n. And the sequence of f of a sub n converges to f of L. Okay? And so what that's saying is, hey, if I have a sequence that converges to L, and there's a function that is also continuous at L, then there must exist some integer n, such that the function is defined at all values of a sub n after that. Okay, so for all n greater than or equal to that n value. And if that's true, then guess what? Then what I can do is I can compare the sequence that I'm interested in to this sequence, the sequence of f of a sub n. And then I know, based on this theorem, that the sequence of f of a sub n converges to the f of L. So if I know, just like in the last example, if I know that this converges to an L, and I have some other more complicated looking function of a sub n, then if these conditions are true, then I can compare this convergence to this one, and I know this must be true. Okay, so again, it's another it's an way we can simplify and deal with more complicated looking sequences. Okay, so here's the proof. Okay, so here's the proof. Okay, so very similar to the last proof. Again, we're going to use the epsilon proof. So the proof starts with an epsilon, right? So here's the proof. So let epsilon be greater than 0. Okay, now, since, again, what are the assumptions? We know f is continuous at L, right? So since f is continuous at L, what do we know? Then there has to exist a delta, right? So we're talking about the limits of functions now. So there has to exist a delta greater than 0, right? So by the definition of a limit, there exists a delta greater than 0 such that what? The absolute value of the distance between the function f of x minus the limit, right, has to be less than epsilon. So that's just using the definition, the epsilon delta definition of a limit for functions, right? Now, if so again, so let's start over. So we're going to let epsilon be greater than 0. Since f is continuous at L, then there exists a delta greater than 0 such that this difference, the absolute value of this difference, is less than epsilon if the absolute value of hold on. Oh, this should be, hold on a second. This should be f of x minus L. No, that's right. That's right. So, oops. F of L. Yeah, I think that's right. Yeah, that's right. Okay. Because, yeah, we're talking about the distance between the two functions evaluated at L. Because, yes, because we're assuming that it's continuous at L, so we can evaluate it at L. Okay. So now, given this, and then if x minus L is less than delta. Okay, there we go. So there's the definition of a limit of a function, right? So again, you may remember this from the limit definitions that you did in Calc 1. Okay, so it all comes back. So again, let's just recap. So notice that this is the definition of a limit, right? The existence of a limit of a function. We start with an epsilon that's positive. And so since f is continuous at L, then there must exist a delta greater than 0 such that the difference, the distance between f of x and f of L is going to be less than epsilon if the distance from x to L is less than delta. Okay? That's the definition that we should be familiar with. Okay, now, so then, since, okay, now here's the other assumption, right? So this was gotten from the fact that we're assuming that f is continuous, okay? We're given that f is continuous. Now, the other thing that we're given is that the sequence converges. Oops. So the sequence converges to L, right? So let's use that. Since a sub n converges to L, what? What do we know to be true? Well, what's the definition of convergence, right? Having a convergence sequence. Well, if the sequence converges to L, then there must exist n, or an integer, a positive integer, or an integer n, right? Such that what? Well, since we're dealing with this up here, right? We also want to make sure that what we're looking at here, because in the definition of convergence, we said, hey, there must be a positive integer n such that what? The distance between a sub n and L was less than some value, right? Now in the definition, we were dealing with epsilon, but here we want to make sure that this difference is less than delta. Okay? So again, delta is kind of taking the place of epsilon in the other proof. But again, realize that epsilon and delta, they're just arbitrary numbers that we're choosing. Okay? So again, there must exist some n, some integer n, such that this is true. Okay? So that's a result. And that's for all n, right? For all n greater than or equal to n, right? Again, that's straight from the definition of convergence. So far we've used the definition of the limit of a function, a continuous function, and also the definition of a convergent sequence. Now, put this all together. What's our conclusion? Well, based on these two things, therefore, we know that for all n, right? So the conclusion is that therefore, for all n greater than n, right? What must be true? Well, now we're going to go backwards. We used our assumptions to conclude this and now we're going to go backwards. If this is true, if we know this is true by definition, then therefore for all n greater than n, guess what? We know that the absolute value of a sub n minus L is, less than delta, right? Which implies, right, if this is true, then this implies, or which implies, right, if this is less than delta, then it implies that what? The absolute value of f of a sub n minus f of L, right, is less than epsilon. Now, why is that? Because we know from here that if this is less than delta, and so a sub n is just a subset, right? Again, just a subset of x, right? So if this is less than delta, then we know that this, which can be plugged in here, can also be plugged in here, so this must be less than epsilon. And what does that mean? So that means we can conclude that the sequence, right? So hence, the sequence f of a, of f sub n converges converges to f of L. And we're done. That's the proof.